Now, I don't know if I can run it because I haven't run it for a while. But let's just set the debugger, and we'll kind of give you a tour here.
Yours looks different from mine.
All right. So what? Okay.
Oh, I'm running main stochastic. You're running main V1.
Okay. All right. Let's do main stochastic
there.
is good. Okay. So
I
think
don't
main
know what the
stochastic.
difference is.
Well, stochastic is what I'm interested in.
Okay.
I actually. Okay. All right. So let's see. All right. So I can even comment this also. So the thing is that we are the point is we want to do several simulations to test this method. So n trial is the number of trials. Let's see, ns. I have to remember what these are. These are all parameters here, and these are the coefficient. I forget which coefficient this is, but I think it's the coefficient of. It's either the coefficient of late or not late. And whoops, sorry, it's not at. It's sharp. And then this one is the coefficient of lateness. If you understand, I think I explained this before. That there's a penalty if the job is late, and there's an automatic penalty if it's late, and then there's a scaled penalty depending on how long it's late.
Right.
So one of these coefficients is the one of the coefficients is the other one, and these are all parameters of the job of the flow shop. I think they're flow shop parameters. Whoops. I'll have to figure out. Well, I'll come back into that, but I think so these are simulation parameters. All right, should I make this bigger?
I can see it pretty well.
Okay, yeah, okay. Probably make it bigger for myself. How come it's not doing what I wanted to do? I thought it was Control Shift Enter. Okay, I can just do Control Mouse Wheel. Okay. All right, so this one is setting up. Did you put in this stuff?
No.
The brakes? Okay, because I don't typically do that. I guess I did it by accident.
Or it may do it automatically.
Well, no, it only. Well, oh yes, that's right, because this was converted from a Jupyter notebook.
Yeah.
That's why. Okay. All right. So this is going to be. So this is. These are simulation parameters. So this is job shop parameters. This is flow shop parameters. Okay. Now I think that. So this is number of jobs, and then number of machines. I don't remember what all the other parameters are. So there are some other parameters. I know that. Oh, I see. I know mu arrival is the mean of the. It's the mean of the known arrival times, and this is the mean of the unknown arrival times. And then so I'm not sure. Case n is equal to I'm not sure, and then AR and mu AR is equal to the mean of known arrival times, and then mu AI is equal to mean of random arrival times. So these are unknown. Okay. I should say mean of unknown. I should say inter-arrival times because it's the time between arrivals. Okay. Okay. I should say it that way. Mean time between known arrivals. And when I mean arrival, I mean arrival of the job.
Okay.
So, for instance, I mean, suppose I know I have a job tomorrow, next Monday, next Friday, next Saturday, right? then you get the intervals from you get the time intervals from those known times.
Okay.
So this is going to be the mean time between unknown arrivals. I should say random. I think that's right, and maybe the other way around. And then mu d int. And this is basically is equal to the mean margin for due time. Okay. So in other words, this is time beyond the. If you think about a job, you have several machines, so you have a processing time on each machine. You have a delay for each machine, and you also have, and so that's the minimum possible time you could finish that job, right? If you, for example, if you have two machines, one machine takes 3 hours, followed by a delay of 2 hours, followed by another machine of 4 hours, then 3 plus 2 plus 4 is the smallest possible time that you could finish that job on time.
Okay.
Now, when you're creating the simulation, you also need to create a due time. So in order to create reasonable due times, we take that sum and then add a random factor that has this mean.
To allow some leeway?
To at least allow some slack. Yeah. All right, so these are all parameters that set the stage. No, go ahead.
It says mean margin for due time. So
yes.
Is that the amount of leeway or
yes.
the total time to take?
That's the amount of leeway.
Okay.
Because different jobs would have a different amount of time. So,
okay, so they would need.
So they need different
amount of time.
So you have to take
leeway.
different amount of time plus leeway. Now for the others, I actually think that it might be better for me to. I know it's in one of these documents on OneNote, and let's see if it's in this one that I shared with you.
That's the one that you shared with me.
Okay, yeah, I think so. So let's see if we can find the variables. They should be here. Simulation model parameters should be here. Yeah. Okay. Yeah. Okay. Yeah. See, this is mu AR. This is irregular jobs. All right, this is not quite right. This is already known. It should be. This should be already known instead of already arrived. Let's see. Might as well.
Yeah. Well,
yeah.
It's.
Oops, sorry. All right, so which, okay. Yeah. I mean, the idea is that you, don't know exactly when these irregular jobs are coming in, but you have some idea of how often they come in. So that's what this one is telling you. I mean, you say roughly every 3 days we get an unpredicted job. So that's what the what the irregular is. Now, how come I'm not in the same place? Let me jump to the PDF. Let's see what else we have. But all the parameters should be here. Let's see. A lot of stuff here.
So even that, I think it's called KSEC.
Yes. I still don't know what that is.
Parameter to introduce randomness in job deadlines.
Yeah, that's the D.
Okay.
So maybe I should call that. That's what the D is. Okay, so this is mu D. Okay. Indoc. Okay. All right, so, it is mu d int, right? Yes. So, okay, so let's see what else we have. Now this one, all right, so here we have average processing time and standard deviation of processing time. I think that's pretty clear. So the jobs themselves are random. So standard deviation means you haven't predicted it. Now, in the simulation so far, we haven't been using this randomness, because even the simple problem without randomness is difficult to know. So I mean, you have time between jobs, and that's generated randomly. But then there's also an additional randomness that the scheduler doesn't know that we generate randomly as well. Does that make sense?
Yes.
And so we have that both for the processing time for each job on each machine, and we also have the waiting time between machines, the information delay between machines. And for each machine we have a characteristic mean time. All right, so let's see what that is. So that would be here you can say so you can see these variables here: mu xm, sigma xm, mu zm, sigma zm. So those are the parameters. So you can see. So these are correspond. Okay. So this here creates a scenario. If you see here, I put 0.001. That just means that these sigmas are small enough that they're basically not even random.
Okay.
I'm not sure why I didn't put 0. I think there was a division by 0 or something like that caused a problem. Okay. So these are, I could say, this is going to be parameters for randomly generating a scheduling scenario. Right. So you can see the end. Well, let's see. Actually, I'm not sure how this. So let's see. Does this have an end trial here? Actually, I'm not sure what this is here, because this is not an instance. This is creating an instance down here. Let me go here. This is creating a particular scenario. Whoops, sorry. Because you have to, each time you run the trial, you create a different scenario.
Right.
All right. So I'm not sure what this does. Let me see what it does. Go to definition.
Oh, that's cool.
Did you not know you could do that?
No.
Okay, good.
I know now.
Yeah, we learn from each other. That's a fantastic feature. I don't know who taught me that. I thought you taught me that. Okay.
Nope.
All right.
Now I know.
All right. Well, here it looks like it's just setting up classes. So Richard is like you. He likes to do things in a very structured way. So you should like his code. So this is to set up. Okay, set up classes. So all right. So this is creating an instance, and you can see what this does. This you can see that it's generating arrival times. This is a random. So this is according to, I can say. Let's see. Sorry. This is randomly generating arrival times generated using an exponential distribution. I don't know if you know what an exponential distribution is, but that's a very common. It's kind of like a normal distribution. It's typically used when you're trying to generate random events.
Okay.
Like, for instance, famous example is time between bus arrivals. If they're random, they're often generated using the exponential distribution. Or time of light bulb failures, time between light bulb failures.
Okay.
No, the exponential distribution is used for that. The advantage of exponential distribution is a normal distribution has two parameters, a mean and a variance. But exponential distribution only has one.
Okay.
So it's kind of easier to control. All right. So here you have arrival time of regular jobs, arrival time of irregular jobs. So that's generating these. So here you're generating a sequence of these. That's why there's a loop there. Let's see. And then here, there. I'm not sure what all this stuff is. I think this is just concatenating all the arrival times together. And then here's generating the random. This is generating processing times. Okay. For this instance. Okay. So I'm not sure why there's 20 here. I think it's just to because sometimes it may fail. And you see the try here.
Okay.
Okay. So I think that's what the 20 is. All right. So I mean, I'm yeah. Okay. So here we're also generating. Yeah, I don't need to get. So this one is generating processing times, and this also does some random distributions. I don't really need to get too much into this. You can see X is the actual set of processing times. Oops, sorry. So this is the actual. And then I don't remember what the K is. Oh, here it says, oh, K-sen is, it says for, K is the number of scenarios. And I'm not really sure what that means. Because we're already doing a number of trials. So apparently each trial consists of a number of scenarios. So at least that explains what K-sen is.
It says K-sen is 1.
Yeah, so K-sen. Whoops, sorry.
You have the K-sen equals question marks up there.
Oh, where did I do that?
After number of machines.
What line number?
34.
Okay. Oh, yes, okay, yes, okay.
Yeah. Just to turn.
Yeah, no, sure, I want to organize. Okay. All right, so I'm not sure what K-sen is used for, but it's there anyway if we need it. So you can see that there's a set of processing times for each scenario. There's two. The first two indices is the there's one for jobs and one for machines.
Okay.
And this is first two indices for jobs and machines. And then you have to do the same thing for the information delay. It's the same. You can see that this code and this code are really the same. I could have done a subroutine, but it's all right. It's not that much code.
You're only running it twice.
And then this is the delay. This is the extra delay. Okay, margin. And then this gives the actual due time. is equal to the sum of is equal to the processing time is equal to arrival plus x plus processing. This is total processing plus total delay, and then plus margin. Not total information, and then the plus margin. All right, so all this is just to create the parameters. And I think, as I said, you're actually generating randomly this sigma x and sigma z, but in the current simulation, these are basically 0 because we're not assuming any randomness.
Right, that's what that 0.0001 is for, right?
Okay, so maybe I'll just say that. So sigma z, sigma x, and sigma z are when jobs exact arrival time. Jobs exact processing and then info delays are not known in the schedule. And that's a whole, we haven't even got, as I keep saying, we haven't even got there yet. Okay. All right, good. So that, I mean, all that is so far conceptually is basically we're setting up the problem. We're setting up the problem so that it, and then we're going to run the algorithm on it. So here we return the instance, and let's go back to flowshot problem main stochastic. So here we are, we've created the instance. All right, now here's the main, it looks like here, I'm not sure what this second index is. I'm really not sure what this second index is. I think this is because this was the KSEN index. Okay, so let's say currently only for one scenario. That's what the 0 is here. And that's the final index. So there will be some code cleaning to do. I think what we were thinking about was that you would change the scenarios for each. You would do multiple. You use some parameters to do multiple scenarios. Oh, I know why. So you need scenarios when you have randomness. When you have unpredictability. So this would be so KSEN is when the where did I put the KSEN here? Was it here or somewhere else? Oh, here it is. So okay. So this would be used if the processing time on info delay times have randomness. So that's why that's there. So that does make sense. All right, good. All right, so now here's where you actually run the optimization. So this is the guts of the whole thing, and this is what you're going to be working in mostly.
Okay.
So here we've got this. Now let's look at what this is here. All right. So did I describe this anywhere?
I believe you did.
Is it up here? Something like, yeah, I think it's up here. So first you randomly generate, and I may need to change this, but I think I mentioned before that the problem is too big, so we can't find an exact solution. So what you do is kind of random exploration. But you want to randomly explore in not just completely randomly explore because there are too many possibilities. All right, so this is what it says here. I'm not sure if this is exactly accurate. And what you'll be doing is running simulations, looking at results, and then figuring out how we can improve the performance. That's because I don't think it's working very well right now. Part of that's diagnostics. It's trying to figure out what it's doing and why it's not working so well.
Okay.
So it's pretty challenging. All right. So first of all, so we've generated an instance. So we know when the jobs are coming in. We know when the jobs arrive. We know how long they take on each machine. We know the information delay between machines. And we also know when they're due. We know all that stuff. We just don't know how to schedule the jobs, what order to schedule them on each machine. So first of all, you just randomly generate some schedules. And I think right now I'm just randomly generating one schedule. So we'll see if that's correct, but I think that's correct. What you do, so here it says iterate ni times. So you're going to take this set of schedules and generate more. And hopefully the more you're going to generate are going to be better. So what you do is, so it's called population growth step. So you're going to have a pool of candidate schedules to modify. Yeah, remember I talked about this last time. You have a pool of candidate schedules to modify. And the number of candidate solutions is NA. So you'll randomly pick one of those candidate solutions. And you increase the age of the solution by 1 because the solutions will age out. If they're there in the pool for too long, you want to take them out because you want to give the new ones a chance to get
be
chosen.
selected.
Yeah. Okay. All right. So then we randomly pick a single machine, and then the thing is that we can solve the single machine problem exactly. There's a way using linear programming that will solve the single machine exactly. And so what you do for that single machine is that, if that machine is in the middle, you don't really know what's going to happen in the future, right? Because it's possible you could shift things around in the future and change the situation. So you basically create some randomized due times for this single machine. Right. Now I really should start drawing stuff. Let's see if I can do this. I have my tablet in my other computer, so give me a second. So let's go to the schedule here. Let's see. It should be here somewhere. You see schedule? Oh, it's not in this one. Sorry, it's in the other one. Here it is. All right, so that was our previous. Okay. All right, so let me see if I can. So this one is 25. So this is the random step in stochastic scheduling. Okay. So here I have. So here you randomly choose machine M. Okay, so machine. So let's say here's my machine M. So these are machines. Okay, so of course you have 1 up to M. Now let's say in machine M we already have a schedule. So maybe this is going to be we schedule first job. I don't know. Let's say this would be job M1. That's the first job. And then there might be delay, and then we have job M2. And then you have job M3. The job M3 might come right after job M2. It's possible. Okay. Do you understand what I'm trying to indicate here? So
each machine has its own order of jobs to perform.
That's correct, yes. Okay.
And so in each iteration, we only change one machine at a time.
No, that's right. That's right. Yes, we only change one machine. But I'm thinking of modifying that, but kind of like that. All right. So we'll have future jobs here, and then you have due times. Now, I don't know when the due time for DM1 is. It might be out here. And then DM2 might be here. And then DM3 is out here. Something like that. Actually, DM2 is pretty close, but that's all right. Oops, I don't know why it's not. Oh, because this thing is there. And maybe DM3 is out here. Okay. Now we want to rearrange this. We want to rearrange this. We want to try a rearrangement. And so what you want to do is you want to guess. You want to guess when each job needs to finish. How come it's not going to do it? Okay. When each job needs to finish. To minimize the lateness, minimize the penalty. Now you can see that we have due times here, but we don't know what happens in between. Right? There's all kinds of stuff that happens in between. So I can't say I just want to finish this job before this time, and I just want to finish this job before this time, because there's stuff that happens in between.
Okay.
So what I want to do is kind of project. I want to kind of estimate the necessary finish times in order that the job won't be late. So I want to estimate the necessary completion times for the jobs for jobs, well, 1 up to n on machine M. So that in order to, so I should say in order to minimize. The penalty. All right. So think about this. Suppose I know the due time for this job is here. Now, when do I have to finish this job JM1 in order to make sure that job M1 finishes in time? Well, I do know that on machine M+1, there's a processing time, XM1, and there's a delay time, ZM1. So that's the delay and the processing time. Now for machine, actually, I should say, since this is on the job M+1, I didn't do that right. Let me erase it. So on machine M+1, I'm going to have I'm going to have a information delay. I think it's called Z, and that's on machine M+1. That's on machine. So I have an information delay Z, and that's on M+1. And it's this for this job, for JM1. And then I also have a processing time on machine M+1 for this job JM1. And then on machine M+2, I also have ZM+2, JM1, and then XM+2, JM1. So let me see if I can type this instead of so we want to predict when a particular job, and I think maybe I'm using too many indices. So let me just say J needs to finish on machine M in order not to be late. All right. So that job J has a known information delay. Okay. I think my notation now is a little bit better. So that would be Z. This is going to be M+1 J on machine M+1. And processing time X. This is M+1 J, and that's on machine M+1. Those things are known. So
okay.
So every job J, I can say every job J. And instead of saying M+1, I can say M+K. Or it might even be, I should just say something like this. I should make another variable here. So M and O, let's just call it Q. And this is Q on machine Q for, and that's Q, it equals M+1. All right, so let me pause for a minute there. So this is the important thing. So I have some job J, and I want to know when it has to finish on machine M. All right. So we want so we know that that job J has to go through the remaining machines. Each remaining machine has an information delay and a processing time. And the job also has a known final due time. So job J also has a known final due time, dj. So what does that mean? There's a final due time, dj, okay. And then I know on the last machine there's going to be xm, and there's going to be information delay. So it takes at least this much time. And then before that, on machine M, capital M minus 1, that's a capital M, xm minus 1, j, and zm minus 1, j. Okay. And then before that, I have xm minus 2j and zm minus 2j. All the way down to the m plus 1 machine. So this would be zm plus 1j and xm plus 1j. Okay. So in other words, in order to finish job J in time, I have to finish before this time. So I must finish job J before this time in the best possible case. Right? I mean, it's going to take at least this amount of time for job J to finish. Okay, so let me just write the equation and then I'll stop again. So that means that job J must finish before dj must finish on machine M before dj minus it's subtract all these z's and all these x's, so it would be x. I guess I said xq plus zq, and this would be the sum for q equals m plus 1 to capital M. So it must finish before this time in the best case, in order not to be late. Okay. All right, so let me pause here. Are you following what I'm saying?
So, is the machine not doing anything while it's waiting for the Z's and X's?
No, the machine is doing something, but I'm only focusing on one job at a time.
Okay.
I'm just considering. Yeah, go ahead.
It's able to perform other jobs, but
yes,
the Z's and X's are the time that it takes for the other machines to do this job.
Yeah, so just focus on one particular job. Forget about the other jobs.
Okay.
Just imagine that the other jobs are worked around in such a way that as soon as job J is finished doing one thing, it can move on to the next thing without any gap.
Okay.
All right. Just suppose that job J goes straight through without any gaps. So once it finishes in machine M, it has to wait a time Z for the machine M plus 1. That's the known information delay.
Okay.
And it has a known processing time on machine M plus 1. And that's the X.
And another thing I have a question about is why do the M's go M minus 1, M minus 2? I'm supposing
because
down.
this is capital M, not small m. This is the final. This is the final machine. That's capital M.
So the first one is capital M plus 1?
No, the first one is small m plus 1. Small m plus 1 up to capital M.
Minus 1.
Right. So you're at machine M, right? So maybe you're at machine M. Next machine is M plus 1. And then you're going out to machine capital M.
Okay.
And on
I
each machine,
okay.
I have a Z. Here I have Z M plus 1 and X M plus 1. And then here I have Z capital M and X capital M. Okay.
I understand.
So, and this, there's a J here, right? Because it's job J. So job J has to pass through all of these states, and then it has a due time DJ. So job J, after it finishes M, it has to pass through this delay and this processing time, then the next delay, then the next processing time. Now, there might be additional gaps, which I don't include. But it's going to take at least this much time to get to finish all the other machines. And then even with all that processing time, I want to finish before DJ.
Right.
So that means that at this time here, I have to allow all these processing times and all these delays before DJ. So that's where the minus comes in. So let me write this a little more neatly. Whoops, sorry. So job J must finish on machine M before this quantity, in the best case, in order not to be late.
Right.
Okay. So is that making sense?
Yes.
All right. So now there may be additional delays. There may be gaps in the processing. Which produce additional delays. Right? Job J may have to wait before it gets on a certain machine. So we want to model. I'm going to model these delays randomly. I'm just going to say I don't know exactly what the delays are. I'll just model them randomly. And I think this is where the problem with the algorithm is coming in, because I think maybe the model I'm using is not so good. But so I have to do this for every. So I have to do this for every job. For every job J on machine M. Okay, so what's my current problem? Actually, I can type now. Okay, so for this machine M, I have I know what the processing time I have for each J. I know what the information delay is and the processing time is for that machine. So I know Z MJ and XMJ. Okay, for each job. I also know this inferred due time, which I'll call D prime. It's the d prime j is equal to inferred. It's not the actual, but it's the inferred due time. Okay, based on the future on the future info delays and processing time. And I also know when that job reached machine M. Okay. So I also know the arrival time of job J on machine M. Okay. So what we really have here now is a single machine scheduling problem. I actually should put this first. Sorry, I don't know why I did that. So this gives me a single machine scheduling problem, which I can solve exactly. All right, now why can I say this? Because I'm not going to change the schedule of the previous machine, of the previous machines at this stage. Okay, in this modification, right? So this is I'm just saying, well, okay, let's assume that the first M-1 machines are okay for the time being, and let's try to schedule machine M in the best possible way for the future. All right. So that means that I know these times. I know in best case, well, I generate these random due times, which is the time I expect it to be need to be finished, and that gives me arrival time, basically processing time and due time, so I can solve the single machine problem.
Okay.
So I can solve that exactly. All right, so that's what's going on here. Yes, here. So that's what this is. All right. So I need you to give me a minute here. So just give me 1 minute. Sorry. Okay. All right, so you missed a little bit there in the recording, but I think you can see this here. So let's see. What is it actually printing? And where is the print statement? So the print statement would be in this stochastic function. And let's see if we can figure out where the print is. Let's see if the print is in here. Okay, yes, okay. So this is going to be, so where does it say print trial? Okay, I guess there's, oh, there it is, okay. Okay, it prints trial every time it tries. So this is number 2. Oh, I see, solution list expand function. So if it prints trial and it doesn't doesn't yield a new one, oh, I see. So so here it says if solution is unchanged, then pass. Okay. So I should say something like this. Here's an if here. I should have an else here. And that would be else. And then I'll say else. And I'll say print. I'll fail. Okay. So this is solution doesn't change. Okay, and then this one I can have, for this one here I can say else. This would be else, say, and let's say print solution, new solution rejected. So let's see what it does now. All right, so there's actually a pretty good mix of no change and new solution rejected. Let's take it up to 3 machines. This is just 2. Let's take it up to 3 machines, or even more. Let's be ambitious here. Let's take it up to, let's see. Yeah, M stage is 2. Let's take it up to 4 and see what happens. And then let's see how many times this is number of trials. That's just 1. And then NS is the number of, this is the number, this is the base number of a solution. And then this is the maximum. This is the maximum number of solutions until pruning. Okay. And then I don't remember what NI is. So not sure what that is. We can find it though, because it's here. I didn't change, I didn't save my changes. Oh yeah, that's right. Okay. So let's go back here. Where did I put it? Oh, I don't need this. I guess it's here. All right, let's go there again. Sorry. So here is stochastic function. Let's see what NI is. Let's match case. Okay. Oh, I see. Well, NI is just the number. Well, let's see. What is NI here? I'm not sure.
Would it be in the overleaf?
Well, no, I don't think so. The overleaf doesn't actually describe this yet. It just describes the situation, but not the function. So it's definitely a loop, but I'm not sure what loop this is. Oh, I see. I guess NI is the number of times you go through this cycle. It's the number of times you go through this cycle of expanding to the age. So we can make that bigger and see if things happen better. So this is, yeah, that's what it is. So I can say the number of evolutionary prunings. We can make this bigger. Let's take it up to 10. I think we probably want to make this bigger also. Well, let's try 30. That's fine. Now, what's going to happen, I think, is that you just never get. After a while, it's going to have no change for everything, and so it won't, or rejected or something for everything. So let's see. All right, so let's do it. So you see, it takes longer now. It's going to get, I should get up to, how many did I say? I said 30. I don't remember what the first index is. But it's still getting new ones. It's hard to see what the values are because they pass by so quickly. I think I shouldn't have had too many. I think 10 was too much. Can I stop this without losing my output? Let's see. I think I can. Here we go. So let's see. So we're down around 648. And you see we're getting basically duplicate solutions, a lot of duplicate solutions, which is actually not bad. Oh, here's a 410, 730, 440, yeah, I see. So where did it start out? Well, I guess there's more on top. Let me reduce the NI to, let's just reduce this to, just so that we can see what's going on. Well, we can do 30 here, and let's just make this 2. I don't remember what this first index is. I thought that would go up to 30 and then repeat, but it's going to 31. So I'm not sure what that is. Maybe it goes up to 40. Let's see if it goes up to 40. Well, here it went to 40, then down to 8.
Yep.
So I guess it goes up to 40, and then it prunes. So this went through how many iterations? 20, 22, 25. All right, so this was up to, went back down to 8 again. So this was on its third. This is on its third try. So we'll try this again. I think 2 is going to be reasonable. Let's actually we can do this a little bit more. I think. Well, it's all right. Let's see what happens. But I don't want it to take forever. Okay, 14, 26. 29, 34, 35, 38, 39. Okay, back down to 13. All right. Good. So we just have to 17, 18, 19, 24. Okay, 27, 30. What's going on? 30. All right, there we go. All right, so let's see what we got. So we look at results. Okay. So let's look at our values. So these are the values. I guess they're sorted, or they're not quite sorted. Well, this one and this one are the same. This is actually not too bad. Let's see. And then this gives the schedules. I mean, this really is giving the information. So let me see. This is called result. So this is result of 2.
Yep.
Okay. So let me look at result of 2. Okay. So let's see. 2 and 4 result of 2. Whoops. How come? Oh, it's small result?
Yep.
Okay. And then let's see. Let's do np.sort. So you got 3 duplicates of this, and 3 duplicates of that, several duplicates of that, duplicates of that. So it actually looks like it's getting somewhere. It actually does look like it's getting somewhere. Um, so what I want to do is characterize the performance, and I'm not sure the best way to go about doing this. And we want to characterize the performance. We want to give some measure of how good this is. And one way to do that would be to graph the best result at each iteration. But I'm thinking that the iterations take longer and longer, so it's going to take a long time to... It may be that we want to change this so that it's not always 30, so that it decreases. Or maybe instead of just saying 30, we also count the number of iterations and restart. Restart if there are too many iterations at one level.
Mm-hmm.
You see what I'm saying? Because I think that if we send this to 2, I think the third iteration may take a long, long time. So we may want to cut off. Main stochastic. I think because they're taking longer and longer each time because, of course, you've got better and better solutions.
Mm-hmm.
The other thing I'm thinking about is here we're only changing one machine at a time. But it might be better, and certainly we'll get better solutions, is instead of just changing the machine M, we also change M+1, M+2, etc. to try to line those up so that they're better.
Mm-hmm.
So that's another possibility. So let's see. Actually, I don't know if this is on the second or on the third or on the first. But it's going to take long. It's going to take. So we'll see. Oh, okay, there we go. So it didn't take that long. And it looks like the best one was 627. Of course, it's random, so it's going to be different each time.
Yeah.
Yeah, 627 was the best. All right. Well, we've been going for quite some time. Why don't we take a break from this? You make it. I'll think about it. You think about it.
Right.
I mean, you see, basically what we're trying to do is, number one, characterize the performance, and number two, figure out how to make it better. So when I get some ideas, I'll write you, and maybe you can play around with the code and try different things.
Okay.
You might put in more print statements to figure out a little bit better what it's doing.
Right.
But I think now you pretty much know your way around the code. And
the comments really do help.
Yeah, and guts is this stochastic function here.
Yes.
So I didn't go into that in detail, but I think that's also organized pretty well.
Yeah, that stochastic function has a lot of comments in it.
Okay. All right, good. All right, so let's break for now, and I'll post this recording.